And now we're going to do a gene mapping question. In this question, we've got three traits. In this case, it is black body, purple eyes, and vestigial wings. Let's kind of skip that at the beginning. So we got three traits, and so vestigial wings is VG, black body is B, purple eyes are PR. And when you do these gene mapping exercises, this is the way it's always going to be, and that you're going to have three traits. Like that's the number that we typically are going to use. And this is the most, I guess, complex or the most steps, the most complicated version of this kind of a problem you could get, in which you're given the data of fly counts from a cross. And so you're going to be told what the cross is. In this case, you got homozygous wild-type fly mated with vestigial black-bodied purple-eyed fly because these traits are recessive, and this is a Mendelian inherited trait. This one that has the black-bodied purple-eyed vestigial is homozygous recessive. Resulting F1 females were test crossed with vestigial black-bodied purple-eyed males, and so another that is homozygous recessive. And these are the progeny you get. And so I'll just take one trait at a time. It doesn't really matter which one you look at. And actually, to even make it simpler, let's just do like A to represent a gene, okay? And so every time that we do these kinds of crosses, let's just say it's three genes, one of the parents will be heterozygous for all three traits, and the other parent is going to be homozygous recessive for all three traits. And the reason why this is the cross that we're always going to do is because when you do this cross, a heterozygous cross with homozygous recessive, we could just really quickly do that Punnett square like this. So here's big A, here's little a, little a. Here's our offspring, whoops, right? So our offspring are going to be 50% are going to be heterozygous and 50% are going to be homozygous recessive. But the useful thing about this is that we can identify the genotype of these offspring from their phenotype. There are not going to be any that are like homozygous dominant, for example. And so whenever we do these gene mapping crosses, it's always going to be a heterozygous parent crossed with a homozygous recessive parent. That way when we get our offspring, like here, we know what the genotype is of all of those individual offspring. So if these traits truly are, totally linked, meaning that every single time that you get vestigial, you also get black, you also get purple, all the offspring should look exactly like the parents. They should be half heterozygous and half homozygous recessive. And so when we look at our data, the first determination that we're going to make is which of these data sets belong to the parents, which of them belong to single crossover events, and which one belong to double crossover events. So because the genes are linked, we assume that whichever cross is the most prevalent or the most common, in this case it's these two, that those represent the traits of your parental generation, okay? Like these are our parents, whichever is the most common. And it's going to be a big difference. You'll notice in this data set, and it's always like this whenever we do these gene mapping crosses, the parents are always way more prevalent than any of the other crossover events. And again, it's because they're linked, they're close together, and so more than likely, we're not going to have crossovers that are going to occur right in the middle of our linked genes, and so that's why the offspring look just like their parents. The ones that are the least common, and so in this example, it'd be this guy and this one, those kinds of offspring, those are the double crossover events. And that is because we assume that double crossover events are the least likely to occur, because that means that we're crossing over 2 times within just the space that these 3 genes occupy. And so that would be less likely. So that's our double crossover event. And then from there, we're going to figure out our single crossovers. So there's going to be 2 single crossover events. And because, if one's, it's complementary, right? And so if one part of the gene goes to the other chromosome, the other part of that chromosome has to come to the other side because they're homologous pairs. And so that means that we're going to have some numbers that are kind of like similar. And so the remaining numbers are 403, 210, 189, and 386. And so these two are close in value, 189 and 210. And these two are close in value, 386 and 403. So these are our single crossover events. Okay, so parental are the most common, double crossover are the least common. The ones in the middle are your single crossover events. To figure out which ones go together, which are the opposite side of the same homologous set of chromosomes, usually they're going to have similar numbers. let's pretend that instead these numbers were really close together. Let's imagine it was like 200, 200, 200, 200. Then you would need to look more closely at your traits over here because we're about to draw what these things actually look like. And you're going to see that for the single crossovers, they should be complementary in terms of who is wild type or who has this recessive trait. Okay, so now I'm just going to go down here and I'm going to kind of start to make some new tables. And so here's my parental cross, right? So my parental cross, we've got wild type, wild type, wild type. And the way I'm doing that is I'm looking up here, wild type, wild type, wild type for this particular one. Okay, and again, that was 2846. Okay, and then the opposite, 2846, 2646 are these guys. And again, that's the same traits as the other parent, recessive for everything. And so we got VG, B, PR, and again, those were 2, 6, 4, 6. Okay, and that was our parental traits. Now we go to the next one, which is the double crossover. So a lot of people like to go parental, single, double, just in terms of, you know, put them in order. That's fine. You can do whatever. I'm going to do my double crossover next. So here's my double crossover. So I'm going to look at my double crossovers. I'm going to go across right here. So I got VG, B, wild type. Now I come down to the bottom. I got wild type, PR. Okay. The reason I'm looking at these two first is because your double crossover is going to let you know which gene is in the middle when we're trying to figure out this linear order. Because we're going to have a chromosome, right? We got a chromosome. There are 3 genes on that chromosome. 1, 2, 3. Remember that a chromosome is an actual physical object. And so pretend that my pencil were the chromosome. We could have a gene here, a gene here, a gene here, and we could say whatever order they are, right? We could say it's gene number 1, 2, 3. 1, 2, 3. Well, this same chromosome, you could pick it up, flip it around the other way, and now we have chromosomes number 3, 2, 1, right? It's the same object. Like the genes are in the same order. And the important thing is that 2 is in the middle. So I could say 3, 2, 1, or flip it over and say that it goes in the order 1, 2, 3, and it doesn't matter. I'm talking about the same object. So when we say linear order of the genes on the chromosome, what I'm looking for is the instructor, the person who's grading you, is I want to know if you have figured out which gene is in the middle. It doesn't matter who's on either left or the right position. What matters is what's in the middle. And so by looking at our double crossover, that will let us know which gene is in the middle. And so when we compare the parents to the double crossover, and I just realized I didn't do so VG, okay, so this one was 21 and this one was 14. I'm going to need that in a little bit. Okay, so when we look at these numbers, we can see that V and G are still next to one another. Wild type are still next to one another. But VG and B, vestigial bodies and black body, they are still close to one another. The thing that has moved is this PR for the purple eyes. And so purple eyes is the thing that is flipping when it is a double crossover event. And so I'm assuming you've already reviewed how double and single and crossover events happen. And so whenever the double crossover event happens, it has to be the one in the middle is moving. Well, in this example, PR is the one that is moving. So what that means is that PR is the gene that is in the middle between these 3. Because when we have a double crossover event, PR, or purple eyes, is the trait that is moving from one chromosome to the other. So PR has to be in the middle. Now I could just put V, G, and B, wherever I wanted. You could have also done it like this and said it goes B, and then PR, and then VG. That's also correct. The important thing, again, is that PR is in the middle. Okay? So that's how I'm going to figure out the linear order is I compare the parents to the double crossover events. Now I got to get the map units. Okay, the map units, remember, are not an actual measurement. You could get out a ruler and measure map units. Map units are a qualitative kind of assessment of the relative distance between genes on a chromosome. And so that map unit distance is based on the likelihood that they are or not going to cross over. And so in order to get our map distance, map units, what we need to do is just add up the probability that we're going to have a crossover event. Okay? So now this is where I'm going to look at my single crossovers. So let me do my single crossovers now. So I'm going to come back up here, right? And for one of them I had plus, and then B, and then PR. The other one was VG, wild type, wild type. That was a single crossover event. and then plus beep here. That's this one. That's 210, and the other one was 189. Okay, that was one of them. The other single crossover event looked like that. Looked like this. It was wild type, B, wild type, and then VG, wild type, PR. And again, that also was, I'm going to put it over here. That was also a single crossover event. Okay, and then let me go ahead and put my numbers. Okay, so this one was the 2. So this one is 403. And then we had 386. Okay, so these are my 2 single crossover events. And one of those single crossover events represents a moment when B would cross over relative to VG and PR. And another one of those crossover events represents a time when VG crosses over relative to PR and B. So I got to look at my information down here and figure out which one represents when VG crosses over and which one represents when B crosses over. Okay? So I'm going to look down here and I'm going to see that PR and B are together, but VG has moved. Right? Like VG is the thing that is no longer on the same side as black body and purple eyes. And so this represents a single crossover event when VG is the thing that is moving. And so this one right here is telling me about the distance between VG and PRB. And then this guy down here, the thing that is moving is B, right? VG and PR on the same side. B is the thing that is moved. And so this one over here is telling me about when this side flips over. So this is going to represent the crossover event between B and VG and PR. Okay, good. So now all I got to do is talk about what the probability is of that to occur. And so when it's VG and PR, so now I'm just going to look up here, and I've got to, instead of using like the raw numbers, I have to use the probability that it happens. Well, in order to know the probability that it happens, I've got to figure out what is the frequency of each of these different kinds of offspring. In other words, how much of the offspring are each type? What is the percent? And so in order to do that, you've got to get your total number of offspring and then just divide however many you have by the total amount. Okay? And so because I've already done this math before, I know that when I add all those together, I'm going to get a total of 6,715 total flies. Okay? And now I got to go back and I got to say, okay, I got a 403. 403 represents how much of the whole? So it would be 403 divided by 6715. When you do that, you're going to get that it is 0.06. Now I do 2846 divided by 6715. I get 0.42. So you're going to keep doing that all the way down the line. And so I kind of prepared this ahead of time, so I'm just going to write in my numbers. So those represent the probability or the frequency of each of these different kinds of events, right? And you'll notice that some of them are really small, right? I mean, like, so we got 0.06 up here, basically like 6% of the time. Some of them for the parental are much larger, 0.42, right? And then the double crossover events, which are really rare, those are really small. That's like 0.0031, 0.0021. That's okay. We're still going to take those into account when we come down here to calculate our map distance units. Okay, so first we're going to do is between VG and the rest of the chromosome. And so I'm just going to take my probabilities up here. Okay, so the probability that I have this occur for this single crossover event, okay, I'm just going to look over here and I'm going to say 210, 189. Well, 210 was 0.03, 189 was also 0.03, right? And so if I take that like as a percentage, that would be 3% of the time plus 3% of the time. And again, that's because I'm looking at this number, 3% of the time. Okay. Now I'm going to add up my double crossover events. You have to include the double crossover because even though double crossover means that more than just that one part crossed over, it still is a crossover event that involves this gap in between VG and the rest of the chromosome. So it'd be the 3, but I'm also going to add in my 0.02 0.31 and my 0.21. And again, we're moving the decimal place here, right? And so 0.31, 0.2, and we add those in. When I add all those together, I get 6.52. Now I'm going to do the same thing over here. This single crossover event, this represents when VG is the thing that is moving, when this side of the chromosome, this side of the chromosome, when it's flipping, okay? And so now I add in my probabilities for that one. So for this one, it's 0.06, so 6 plus 0.06, 6, and then I include my double crossover. Because the double crossover with 3 genes is only going to happen with like 2 sets of data, that means I'm going to end up adding the same numbers again. That's okay. Okay, so now I got 2 numbers. I got 12.52 and 6.52. So now I'm going to draw my chromosome again. So here's my chromosome. Again, PR is what is in the middle. I'm going to put VG on the left. I'm going to put B on the right. You could have flipped VG and B. It doesn't matter. PR needs to be in the middle. Okay, 12.52 represents when VG is crossing over relative to the other two. And so 12.52 is the distance between VG and PR. Because again, that's the likelihood that this is going to flip relative to this section of the chromosome. So those are my map units, 12.52. Over here I got 6.52, and so those are my map units between B and then the section of the chromosome that contains VG and PR. So these are my map units. And so this was several steps, obviously, but the way that you got to do it if you're starting with raw data, just to get going, you got to identify your parents, your double crossovers. Those will allow you to figure out the linear order of the chromosomes. Now you got to come back to your single crossover events, match them up, and then get your frequencies for each of the events. Now that you got your frequencies for each of the events, you're going to come down here, you're going to identify which single crossover represents which portion of the chromosome, and now you just add up your corresponding probabilities. And those are going to give you your map units. The next part of the question, the next thing we could potentially calculate, is the coefficient of coincidence. The coefficient of coincidence. And so, you know, everybody teaches this in different ways. I don't really require people to memorize formulas. I don't see the purpose in doing that. And so I'll tell you what the formula is. And in order to get your coefficient of coincidence, C is going to equal your observed double crossover events divided by your expected double crossover events. But your expected double crossover events are equivalent to the frequencies of the 2 single crossover frequencies multiplied together. So it'd be single crossover times single crossover observed, right? Frequencies. And so I'm just going to plug all of that in. So my double crossover observed is 0.0052. And I got that because if you add your 2 double crossover frequencies over here together, that's what you get, 0.0031, 0.0021, that equals 0.0052. So 0.0052 is my observed double crossover. And now I'm going to multiply my 2 single crossover observed. And so for me, it was 0.06 multiplied by 0.12. And again, those are my single crossovers. The way I got that is by adding up my individual single crossover frequencies. And so this guy was 0.03, this one was 0.03, whoops, sorry. This one was 0.03, this one was 0.03, add those together, that's 0.06, right? And then for this one, I got 0.06, and then 0.06, add that together, it's 0.12. That's how I got my 2 observed single crossover frequencies. Now that I got all my numbers, I just plug it into the calculator and solve. And when I do that, I'm going to get 0.72. So 0.72. That is C. Okay. Now that I got C, I can get my interference. Interference is easier. It's just 1 minus C. Well, I already know what C is. It's 0.72. And so my interference is going to equal 0.28. right? So C is 0.72, interference is 0.28. As long as your numbers on the other side are correct, you know, you've done your correct calculations of frequencies, this should be pretty straight forward for getting your coefficient of coincidence and your interference.